Hello there and welcome to a brand new lesson. This is How Beyond Numbers, where we learn maths the easy way. In this lesson, we are looking at rational functions. And specifically, we are looking at the domain and zeros of a rational function. By the end of this lesson, you should be able to define a rational function as a ratio of two polynomials. You'll be able to find the domain by excluding values that make the denominator zero. You'll be able to find the zeros of a rational function by setting the numerator equal to 0. And we will form a foundation of tackling asymptotes. Here are some vocabularies we'll be using in this lesson, and I advise you quickly pause and then take a glance before we proceed. Without much ado, let's quickly go into it. So let's start by looking at what a rational function is. When we talk of a rational function is simply any function at all that can be written as, so a rational function r of x equals p of x over q of x. What we mean is the p of x, which is the numerator, is a polynomial. The q of x, which is also the denominator, is a polynomial. And you just make sure that the denominator is not equal to 0. We know what division by 0 does. It gives us an undefined function. So any function at all with numerator and denominator, where both numerator and then denominator are polynomial functions, then we can say that is a rational function. For example, if we take f of x is equal to x plus 2 all over x minus 3. X plus 2 on the function graph is what we see over here. So this is x plus 2. So on our graph, as you can see, this is the x plus 2. And then this, on the other hand, is x minus 3. But we are writing them together as a function. You see, and we are calling that a rational function. So for the rational function, they combine to give us this, as you see over here. You see, so if I zoom out, you see how the function is going to look like. Yes. So there are so many characteristics that will come, or that we'll look at as we go through this course. Our second example here is what we have as g of x. So it says g of x equals 2x squared minus 5x and then plus 1 all over x squared minus 4. This is a polynomial of degree 2. And this is a polynomial of degree 2 as well. The previous one we did, they were both polynomial of degree 1 each, you see. But this, on the other hand, is a polynomial of degree 2. And this is also of 2. So on our graph, let's look at how it will look like. So as you can see, this, on the other hand, is the graph of this polynomial function we have over here. And then looking at our last example, we have h of x, which is equal to 1 over x. That is also another rational function. And this is its graph as shown. So now that we know what these rational functions are, we want to focus on the domain and the zeros of the rational functions. So let's first of all talk about the domain of the rational function. When we talk of the domain of the rational function, it's simply all the real x values. All the real x values except those that will make q of x equals 0. And we said rational functions, that is r of x, are written as a p of x over a q of x, right? So any number or any value of x that will make the denominator 0 is not part of the domain, because if the denominator is 0, then we have what? We are going to divide by 0, and mathematically that is incorrect. Hence, we are saying the domain is all real values of x except those for which q of x equals 0. So if you want to find the domain of a function, all you do is you equate the denominator to 0, and then exclude the values of x that you get. So for instance, if you have 3 over x minus 5, and then we want to find the domain, what we do is we equate this denominator, that is the x minus 5, let's equate it to 0. And if x minus 5 is equal to 0, make x the subject, you have x equals 5. So it means any value of x is going to make it defined, but not 5. Then you say, therefore, our domain is what? R except 5. You see? Or you can easily say x is an element of all real numbers, but then x is not equal to 5. Now, graphically, what happens when we approach 5? What happens when we approach 5? So this is the graph of the function 3 over x minus 5. And if I'm to zoom in, let's look at what happens. So even from 0, we have corresponding values of y. You see, we have corresponding values of y. 2 has, 3 has, 5 has, 4 has. And then from the right hand side, also towards our left, we have all these numbers that have corresponding values of y. But then what happens to 5? You see, as we are on 5 now, you realize that all the values are trying as much as possible to get away from 5. So if you look at the blue line, it is not getting to 5. You see, even if you choose to go up, it will still not get close to what? 5. In our next lesson, we'll look at why this is so. That is, we call it the asymptotes. We'll look at that into details. Now let's look at what we call the zeros of a function. If you have a rational function and you want to find the values at which the values of x at which the rational function equates to 0, what we do is we equate the numerator, that is the p of x, to 0, and then we do what? We solve. But you should make sure that that value of x that makes the numerator 0 shouldn't also make the denominator 0. You see? So we equate the denominator to 0. For instance, if we have f of x, which is equal to the x minus 2 all over x plus 3, that is our f of x. All we need to do if we want to find the zeros is to equate x minus 2 to what? 0. And equating x minus 2 to 0, we have our x being equal to 2. You see? Now, graphically, what does this also mean? So graphically, this is the function x plus 2 all over x plus 3. Now, when we say the zero of this particular rational function, then at where do we have the rational function having a y component of 0? This is our y-axis, you see, and then y equals 0 at this point. But if you have to trace it to where it intersects the function, that happens at x equals 2. If I'm to zoom in, you realize that the line touches at this point. And this coordinate is 2, 0. 2, 0. And at that particular point, the function evaluates to 0, or y equals 0. Or you can even call it the x-intercept. You see, so this is what it means graphically. So simply put, if you want the domain of a rational function, equate the denominator to 0 and exclude the value that gives you the denominator to be equal to 0. So as a matter of fact, for rational functions, their domain is all real numbers except that particular number that makes the denominator 0. If we come to the zeros of a rational function, we equate the numerator to 0. With that said, let's solve some questions to enhance our understanding. So our first question here, we have to find the domain and the zeros. It says, for f of x equals 3 over x minus 5, find first of all the domain. And then secondly, find the zeros of this rational function. So how do we go about it? For the first one, first of all, we know f of x is equal to 3 over x minus 5. You see? So if it is a domain we want, the domain, the domain will be all values of r except that which makes the denominator equal to 0. You see, so for the domain, let's equate what our denominator x minus 5 to be equal to 0. Making x the subject, we have our x which is equal to 5. So as we are saying, all values of r, we say it implies that the domain is what all values of r excluding what 5. Or you can rewrite it as x is such that x is an element of r, but then x is not equal to 5. Any of these notations are correct. I'm sure this is what you are used to. So x is such that x is an element of r, but then x is not equal to 5. Then we come to the zeros. So for the zeros, what do? We equate the numerator to be equal to 0. Now, our function once again is 3 over x minus 5. The numerator we have here is a constant. You see, it can never be 0. We know 3 is not equal to 0. So it simply means that the graph never crosses the x-axis because there is no way it is going to give us 0. You see, so the graph never crosses the x-axis, or there are no zeros, which implies that the graph never crosses the x-axis. If you want visual confirmation, let's quickly plot it out. So this is just a section of the graph, and as you can see, it starts all the way here and it continues to move, but it never touches the x-axis, even towards the left. The same applies to the right. It will just continue to move closer to the x-axis, but then it will never touch it. You see, so that is it for our first example. And there are some examples that would even lead you to actually factorizing. Hence, when it comes to rational function, you should have mastered the act of factorization, which is on this course as well. If you need help, you can quickly check the playlist and then quickly brush through that. So for our second example we have here, it says you have to find the domain in zeros of the function g of x equals x minus 2 all over x squared minus x plus minus x. So our g of x is equal to x minus 2 all over, we have an x squared minus x minus x. So for the domain, just as we saw for the previous one, then we would have to equate the denominator to 0 and then exclude those values that makes our denominator 0. So we have, for domain, we have our x squared minus x minus x, which is equal to 0. We then need to factorize this. Now, if you factorize this with the method of factorization we've done so far, you get x minus 3 and then the x plus 2, which is equal to 0. You then equate x minus 3 towards 0. Hence, our x is equal to 3. Then x plus 2 also towards 0. And our x is equal to a negative 2. You see? Hence, we can say that the domain, which is in terms of x is such that x is an element of all real numbers, but then the x should not be equal to 3, and then the x should not be equal to negative 2. That is all. Or better still, you can write your domain is what? All element of R excluding let's set -2 and then 3. Any of these are correct. The next one says we want our zeros. So for the zeros, what do? We equate our numerator to 0. That is x minus 2, which is equal to 0. And our x is equal to 2. You see? So the zeros of this function, g of x, are what? Or s. X is equal to 2. Let's quickly look at what this actually means on the graph. So this is the graph of this particular function, as you would see. Now, we said the domain are what? All element of R except 3 and then -2. So let me zoom in to -2 and let's look at what is happening over there. You see, this is -2. If I'm to put a vertical line over there, you realize that the function that is from this side and then both of the side, they try as much as possible to avoid touching it. Do you see? Now the next one was also what? 3. So if we come up here, this is our 3. If I'm to draw a vertical line, you realize that the function also tries as much as possible to avoid this 3. Then talking of the zeros, that is where the graph touches the x-axis. If I'm to zoom this as well, you realize that it touches it at 2. So with this calculation, you don't necessarily have to come and then draw before you can determine zeros and domain. Just by knowing the steps, you can easily predict the zeros and then domain and even other properties of the function, as we would see in our next lesson. So this is going to be the last example we solve, and it has to do with simplification. It's not always that we just quickly go and then find our domain and then zeros. Sometimes you need to pay critical attention to what you have before you. So let's look at our last question we have here on our screen. It says for h of x, which is equal to x squared minus 4 all over x minus 2, we have to find the domain and the zeros. The domain and the zeros. So with our h of x being x squared minus h all over x minus 2, let's look at the domain first. So you know for the domain, it is all values of r except those that makes it undefined. So we are going to equate the denominator to 0. So our domain, let's equate x is x minus 2 to be what? 0. Solving for x, we have our x, which is then equal to a 2. So for our domain, we'll say x is such that x is an element of R. That is all element of R. But then x is not equal to 2. Because if we put x equals 2, we are going to get what? An undefined expression. With that said, let's look at the zeros. So for the zeros, what we do is we actually equate the whole numerator to 0. Our numerator is x squared minus 4. If you want to rewrite this, this is actually difference of 2 squares. That is x squared minus 2 squares. Hence, we can factorize it as x minus 2 and then x plus 2. And we said we are equating them to 0. Making x the subject, we have x equals 2 and then x equals -2. These are the values that actually make our function 0. But then if we look at it carefully, looking at our domain, x equals 2 shouldn't be part of the domain. You see, x equals 2, it shouldn't be part of the domain. Hence, this leaves a hole over there. It's because it is not part of the domain. If we put it in the domain, we are going to get what? Undefined. Hence, it is not part at all. So this implies that we are only going to stick with what? The -2. So we'll say For the zeros, our zeros are what? Or is x equals -2 only. Because for x equals 2, it is a whole. Now, what do we mean by a whole? Let's quickly go to the graph so that I'll demonstrate to you. So graphically, this is the representation of x squared minus 4 all over x minus 2. It actually looks like a straight line. Why? Because if we were to rewrite this, we have x minus 2 and then x plus 2 all over x minus 2. And it would look like this, cancelling out this. Hence, we have x plus 2 only. You see, that is why the graph actually looks like a straight line. But then if we are to analyze it carefully, you realize that even though it is a straight line, it is not continuous. There are holes in there. You see, so this is a hole. And for the 0, this was the 0. That is x equals -2. A cut, or we can even call it the x-intercept. But for x equals 2, you see what happens? The line doesn't continue over there. It reaches and then pause, and then skip, and then continue. So we call this a hole. In our subsequent lesson, we'll talk more about holes, discontinuity, and all that. In this lesson, we have spoken about the domain and the range. When it comes to the domain, it is all of the real numbers except those for which the denominator is equal to 0. Then when it comes to the zeros, it is what makes the numerator equal to 0, because you know for a fraction, if the numerator is 0, that is all you need to make the whole fraction equal to 0. On that note, I'll leave you with some exercises for you to try just to test your understanding. So here you have 4 questions based on all that we've done so far to test your understanding. Let's have your numbers so you learn maths the easy way. If there's any issue of concern, you can always let me know at the comment section. If this is your first time on this channel, I think it will be of help to you. You can subscribe if you so do wish, so that anytime I release a video, you'll be notified as well. See you in our next lesson, and bye for now. Do stay safe.